Hi everyone, welcome back. We are now in week 3 of biostatistics, and we are going to talk about two topics which are really important for understanding why we go about doing more complicated analysis beyond just looking at bivariate analysis. And two of the main reasons we do that, particularly in observational studies, is we want to address potential confounding from other variables in a relationship. So far, we've only looked at bivariate associations, something that we might also call crude associations, and we're going to move towards what we call adjusted analyses that take into account multiple variables simultaneously. But before we do that, we need to understand the concept of confounding. We're also going to talk about effect modification, which is different than confounding, and we'll explore what that means. Effect modification is something that's actually really interesting that we hope to report out, whereas confounding is usually something that's kind of a nuisance that we want to address through statistical methods to reduce the amount of confounding, as we'll see here momentarily. So as we discussed earlier, in the context of looking at contingency tables, often we're interested in some sort of exposure-disease relationship, and we might do something like calculate a relative risk to assess the relationship between the exposure and the outcome. Well, as we know from epidemiology and public health, most things don't have a single factor in terms of disease progression or disease onset, and we know that they often have what we call complex etiologies or complex causes. And so we often want to consider what are the multiple factors that are involved. And also sometimes those factors that are involved could be interrelated in themselves. For example, health risk behaviors tend to cluster. So we may have people who smoke and also drink alcohol, or maybe have other lifestyle factors that all contribute to a disease state. And it can be very difficult to assess their independent effects on some outcome. As I mentioned, case control studies and cohort studies were used to isolate the effect of smoking on things like lung cancer, but it was very hard to prove that there was not an association with other things that might be related to smoking, such as a poor diet or other things. That's not to say that everyone who smokes has a poor diet, but there are things that may be disproportionately found among those who have certain health risk behaviors. So we want to take into account multiple risk factors simultaneously whenever we're considering looking at exposure-disease relationship, or really between any independent variable and a dependent variable. We want to consider other factors that might be involved. So a confounder is always related both to an independent variable of interest. Often when we design a study, we have one or two exposures or other factors or treatment that we're primarily interested in assessing, but we also want to take into account these other variables. So a confounder is related to an independent variable of interest and also to the outcome. Okay, so even if in theory something might be related to the independent variable, unless it also has a relationship with the outcome, it will not be a confounder. When adjusted for statistically, the relationship between the individual variable of interest or the independent variable of interest will change, or what we say become attenuated. Often this will mean that the effect is lessened once we adjust for the other factor, but the reverse is also possible, although we're not as concerned about those kinds of confounding, which we call suppression effects. Normally what we're doing is trying to get an adjusted estimate after taking into account factors like age and other things that are known to be related to the outcome of interest. Age is often a confounder of certain health risk states because, as we've talked before, age is associated with most health outcomes. In some cases, the variable of interest will be determined to have a spurious relationship with the outcome, meaning once we account for the confounding variable or multiple confounding variables, its effect disappears. And this is why we don't want to stop at doing bivariate analysis and reporting our crude results. We often want to select variables that might be potential confounders. And this process, again, leaves a lot of room for the analyst to make decisions. And so we do want to start with an analysis plan and have it guided by either the previous literature or also standard methodologies for addressing confounding. So how do we assess for potential confounding? Well, first of all, we can explore bivariate relationships between independent variables among each other, and then also their relationship with the outcome. So one of the purposes of what I was doing in table 2 of my own little analysis was to say, what are the relationships with outcome? What are the important factors? And this is something you looked at in homework 2. Well, one reason we want to do that is we want to know everything that could be related to the outcome. And if we have something that we're primarily interested in terms of its relationship with outcome, if it's related both to that exposure and to the outcome, then we want to make sure that we include it as a potential confounder. So if an independent variable is associated both with the outcome and another variable, it could be a confounder of that variable's relationship with the outcome. Can also look for confounding based on known clinically meaningful associations. What that means is that if the prior literature suggests that we should be adjusting for things like age or other health states or other risk factors, even if we don't observe a statistically significant relationship with a variable and the outcome, or the variable and the independent variable, it's a good idea to include certain known confounders into a model. Once we put lots of variables into a regression model, which we're also going to talk about this week, we want to make sure that it's possible that those effects will only come to light when we do a multivariate analysis. So if it is a known confounder, it should be there, and often the reviewer of a scientific article will be looking for certain things that we should be considering as potential confounders. So let's start with a concrete example. We want to know the association between obesity and incident cardiovascular disease, okay? And so from a 2x2 table, we calculate a relative risk associated with obesity of 1.78. What that means is that those who were determined to be obese based on BMI had a 1.78 times increased risk of developing cardiovascular disease over the period of the study. So almost a 2 times risk, which may not sound like a lot, but that's that would be considered an important enough risk factor that you might want to develop some sort of intervention around, or we all know that there is an association between obesity and cardiovascular disease. Anyway, so this wouldn't be a big shocker, but the relationship here that we found was that it was 1.78. Now notice that this is a crude association. We've simply looked at obesity status versus the outcome incidence of cardiovascular disease. So one way we can detect potential confounding is to look at what is the relative risks when we stratify on a potentially confounding variable. So we're going to stratify here by age less than 50 and age greater than 50. And even if we were to ultimately include age as a continuous variable in our analysis, this is a good way to visualize the potential confounding effects of another variable. So remember, our crude relative risk was 1.78, okay? And that we're going to go ahead and say was also statistically significant. We see when we stratify the results that the relative risk among those less than age 50 is calculated to be 1.43, somewhat lower than the overall. And likewise, in the older age group, we also get a very similar relative risk of 1.44. So this situation where we see that the crude relative risk is actually higher than either of the two stratified relative risks, this is a sign that there's confounding. And what it means is that age is also related to incident cardiovascular disease. And obesity is overrepresented in the older age group. And it's a little hard to see that just by looking at the counts here. But just by simply doing the stratified analysis, we can often detect confounding. And we can have the statistical software calculate an adjusted relative risk for age. Now, I'm not going to formally perform that here, but my guess is it's going to come in at around 1.44. That seems to be where the real relative risk is. So if we had reported the original relative risk, the crude relative risk, we would have failed to address for an important confounder, which is age, which is related to both obesity and to cardiovascular disease in this case. So that's another sign that there is actual confounding happening. And let's suppose that our adjusted relative risk is 1.44, and our original relative risk was 1.78. Usually we say that there was meaningful confounding when the relative risk was changed or attenuated by more than 10% of the original value. So in the case of the relative risk of 1.7, we have a 0.34 change. So a 10% change would have just been about a 0.18 change. And what we actually saw was about a 0.3 change. So this is definitely a case of confounding. And all I was saying there is that a 10% change in our estimate of the relative risk would be evidence that we had confounding once we adjusted for it. Okay. And even if that was less than 10%, if there was a relationship that was potentially confounding, we would want to include something like age in a final multivariate model. Okay, so we can think about this schematically as age is a predictor of cardiovascular disease risk. Age is also associated with obesity. Obesity has an independent effect on cardiovascular disease risk, but it's somewhat attenuated by the fact that age is both related to cardiovascular disease risk and to obesity. So it could be driving both of those. Not completely so. We saw that there is some direct relationship left after we've taken into account age. However, age is possibly explaining both of these, and thus our observed relationship between cardiovascular disease risk and obesity. So this is one example of confounding. So we often use our bivariate analysis to inform our multivariate analysis. And so we want to identify all those factors that could be potential confounders. If something is associated with both the outcome and other exposures, it could be a confounder. So we would want to include that in a final model. So in homework 2, when I said what were the most important variables, what I really meant were what are all the things that are related to the outcome that we may want to use in multivariate analysis. So moving now to effect modification, which might be a little less familiar than the concept of confounding. I think any of you who have taken science courses or thought about different phenomena, you realize that there's multiple factors that once you take into account another factor that may influence the relationship. But effect modification is actually something that's really interesting, both scientifically and also to readers who may want to know if there's important, let's say, subgroup differences in effects. So confounding is kind of a nuisance that we hope to eliminate through statistical adjustment. It's kind of an artifact of the fact that we can't always do purely experimental studies, and we should account for all the other things that are different about two populations, something that we call selection bias. So confounding, again, is usually just considered a nuisance issue that we want to address with statistical adjustment. Effect modification is actually really interesting. It means that the effects that we observe vary depending on levels of another variable. Okay, so this would be often in terms of subgroup differences. So I'll give you some examples of where this might happen. Looking for effect modification should be part of the analysis plan, however, preceding actual analysis. it would be really easy to make all kinds of different subgroup comparisons, whether it's by age or by sex or by race, ethnicity. So these should be spelled out in advance before we just start looking for differences among subgroups. Subgroup differences will emerge by chance alone. And don't forget, when we set our p-value of 0.05, usually that's based on making one comparison, one statistical task. So if we start making all kinds of other subgroup comparisons, not just on the entire sample, then we might get ourselves in a little bit of trouble as far as type 1 error. So we can minimize type 1 error by making as few tests for effect modification as we can, but if we go into a study thinking there may be effect modification, it's reasonable to look for it. So for example, if we had found that the relative risk of cardiovascular disease given obesity in women was 4.4, and the relative risk for cardiovascular disease associated with obesity in men is 1.2, this would be a different situation. Notice that the value of 1.7, which was our overall effect, falls between 4.4 and 1.2, okay? And it might be a reasonable average of the effect of women and men combined. However, the effects are different between women and men. It seems like obesity is a more important predictor of obesity in women than it is in men, okay? And so you might think, well, this is a variable influencing the outcome, but it's not diminishing the effect. It is simply saying that the effect is different across different groups, and our average effect of 1.7 may still be true. So this might suggest something like that there's a different biological mechanism for cardiovascular disease in men and women. You wouldn't want to speculate too much as to why that would be, but it could be that while something is a risk factor among men, it could be not so much in women and vice versa. It could be that men have other risk factors that women lack. So heavy smoking might be an example, at least historically. And so maybe that risk factor kind of swamps everything else. And so maybe the obesity doesn't seem to have as much of an effect as it does among women. Or it could be a chance finding. And that's one reason why I said we don't want to make tons of subgroup comparisons, because each time we look at a subgroup and perform a statistical test, we're having that risk of making a type 1 error. That's why it should be informed from sort of more theoretical perspective or a clinical perspective, where we should think of biologically plausible reasons why there might be subgroup differences. It's really tempting if there's a null finding to say, hey, what about this group? And again, this is why we should pre-plan these comparisons in advance. So this would look a little bit different than what I showed you with age, where age was confounded with the relationship. All we're saying here is that in these different strata, the risk associated with obesity is different. So in the case of men, the relative risk 1.2, relatively weak effect. We'd say that's only a 20% increase in risk of cardiovascular disease. But among women, the relative risk is 4.4, meaning a 4 times increased risk of developing cardiovascular disease given obesity. So this is really interesting and actually might point to, again, different mechanisms, different biological pathways that produce cardiovascular disease. And we should want to report out this difference. And so normally what we would do is, if we found differences as pronounced as we see here, is actually report the separate stratum-specific results for men and women. We could also present a pooled estimate for the two groups together, but we would want to highlight the fact that there was this difference between the two groups. So again, confounding is when one variable explains away another variable. Effect modification is when there's differences across, let's say, categories of another variable, and it's actually something that's very interesting to us. Okay, so like I said, we may want to present separate risk estimates for men and women, especially when they are different as they are. If it's only slightly different, we would want to present always the pooled estimate with maybe a formal test for effect modification which we can do, which is called a test for the homogeneity of the odds ratio, or basically, is the odds ratio the same across the other factor? We won't do that in this class, nor will I test you on that concept, but just know that there is a way to formally test for a statistically significant effect modification. There is not such a test for confounding. It's more just an assessment of what happens to our effect in the presence of another variable. Okay. And like I said, this is actually a clinically or epidemiologically interesting finding when we look at effect modification. It could suggest hormonal differences, it could suggest sociocultural differences, and so we do want to report that whenever we see it. In terms of statistical adjustment, 2x2 tables are one way that we can actually do this. We can actually use what's called the Cochran-Mantel-Hunsel method, and we could simply create stratified 2x2 tables and get an adjusted odds ratio or an adjusted relative risk using the Cochran-Mantel-Hunsel method. And I suggest often doing this when we're learning to do multivariate analysis, because it allows you to kind of see what's happening to the main effect or the crude effect as you adjust for other variables. The problem with stratification is that at some point, some of those cell counts can get really small. And so we will probably want to eventually move over to using some sort of other tool, which we'll get to when we go to logistic regression or linear regression. But it is a good way to visualize and test for interaction and confounding by looking to see what are the stratum specific estimates. And if it looks like a good average of the two strata, then we would say that there is either effect modification or that there isn't confounding. If it falls outside of the two strata, like we saw with age, that's an evidence of confounding, and we would want to create an adjusted estimate. Okay, so when we adjust for something, we can get a pooled estimate, meaning a combined estimate across strata that's adjusted for this other factor. And sometimes it's fine to stop there if we have relatively few measures in our study. We could just use a series of 2x2 tables stratified by other variables. However, what we're going to learn next is how to use more powerful tools like linear regression and logistic regression to do very similar work. So when we're testing for effect modification or looking for effect modification, sometimes we have to make sure that we don't just use our eyes, and we do make sure that there's a really meaningful differences happening. So here's an example of where in a treatment study, we see a difference between placebo and a new drug among men and women. Among women, it looked like there was no effect of the new treatment, whereas in men, it does look like the drug is having an effect on HDL, which is the good form of cholesterol. So just based on this visualization, it looked like, oh wow, well, while there's no effect in women, there is an effect in men. But if you look at the stratified table here, in this case, we're looking at a continuous outcome. We can see that our sample size among men is pretty darn small. We only had 10 in the new drug group and 9 in the placebo arm. And so even though there is this difference in mean HDL, we would want to make sure that this was statistically significant before reporting any kind of effect modification. So we can do that statistically to see if this difference is real. But again, we should have stated in advance that we anticipate a difference by sex and not just look at subgroup differences. It'd be really easy to keep cutting our data in half by all kinds of things, including age groups and things like that. So it should be planned out in advance. And if it had been planned out in advance, we would have tried to recruit an equal number of women and men into the study if we expected there to be differences, especially if we expected there to be a stronger effect in men. So that's another kind of cautionary story of why we want to determine in advance what we're looking for as far as effect modification. Okay, so confounding and effect modification can often best be explored using 2x2 tables. And using dichotomous categories as opposed to the original level of measurement is really useful for detection of confounding and effect modification, even if later we decide to use other versions of that variable, meaning we might use the continuous measure for age as an adjustment in a final model. Just using 2x2 tables on dichotomous measures is one way to explore confounding and effect modification. So as I mentioned, looking for confounding and effect modification results in lots of analytical decisions on the part of the investigator and on part of the biostatistician. So that part of analysis should, again, be a part of an analysis plan. And so when we have a data set, we often will determine before we do the study what variables we are going to include or look for potential confounding and effect modification. It is also important to sometimes, if we have an unexpected effect of confounding, to report that out, because we wouldn't want to present a result as being positive that was actually confounded by another variable. So it is possible that we will find variables in the process of doing the work that are important confounders. So we should have some flexibility as we're doing analysis. And the literature is often a good guide to determine what should be included in a study as far as potential confounders. So one reason we do an extensive literature review before we start doing our own research is to identify those variables that may be important to capture. Because if we simply presented crude results, there would always be the question, is this relationship possibly spurious, meaning there really is no relationship at all? Or to what extent is it overestimating the effect because we fail to address important confounding? Probably fewer questions about effect modification, but again, we always want to make sure that we've done our due diligence in preparing to do research by reading research done previously. So really, this is just a brief introduction to the concepts of effect modification and confounding, something we're going to explore more as we move into logistic regression modeling and linear regression modeling, which is next.